Welcome, everyone. Today, we are going to explore a topic that sits at the very core of modern high-performance systems, the Go Concurrency Paradox. As developers, we are drawn to Go because of how effortlessly it handles concurrency. Go routines are lightweight, easy to spawn, and represent one of the language's greatest strengths. However, as the visualization on this slide illustrates, there is a fine line between organized parallel execution and total chaos. The ease of creating Go routines is a double-edged sword. Without careful management, the simple, streamlined logic we start with can quickly devolve into a tangled web of race conditions, deadlocks, and resource leaks. In this session, we will move past the basic syntax to master the hidden dangers of Go routines, learning how to build concurrent systems that are not just fast, but fundamentally robust and predictable. Let's dive in. Go's superpower is, paradoxically, also its greatest weakness. The language's widespread adoption has been driven by its approach to concurrency, making it a first-class citizen. Go routines are designed to be lightweight and easy to launch, providing developers with a powerful toolset for building modern, high-throughput systems. However, this inherent power carries a hidden cost. Because concurrent programming is made so accessible, it frequently results in data races that can be devastating to production environments. To illustrate this, the Uber engineering team noted a recurring and painful problem, stating that outages caused by data races in Go programs have brought down critical customer-facing services for hours. These incidents cause significant inconvenience to customers and have a direct, negative impact on revenue. The problem we are discussing isn't merely theoretical. It is happening right now at a massive scale. To quantify the scope of this challenge, consider Uber's implementation of a dynamic race detector across their entire Go monorepo. The sheer volume is staggering. They analyzed 46 million lines of code, powering 2,100 distinct microservices. This process uncovered more than 2,000 data races. Addressing these issues required a monumental effort, with 210 developers successfully fixing over 1,000 data races in just 6 months. These figures reveal the true scale of the challenge and the intensive resources necessary to maintain code reliability in such a complex ecosystem. It is often said that a bug is just an undocumented feature. But in the case of Go, a study by Uber suggests that certain data races are actually inherent to the language's design. The most surprising takeaway from this research is that data races are not merely common concurrency errors. Many are directly facilitated by Go's specific idioms and nuances. The study concludes that several language design choices, when combined with the extreme simplicity of introducing concurrency via Go routines, make Go highly susceptible to data races. Essentially, the low barrier to entry for concurrent programming can mask underlying complexities that lead to memory safety issues. Looking at the idiomatic Go patterns shown here, we can identify 3 main contributors to this problem. First, transparent capture by reference enclosures often leads to Go routines sharing variables they shouldn't. Second, the underlying semantics of slices and maps can be confusing, as they often behave as references even when they appear to be passed by value. Finally, the sometimes indistinguishable difference between value and pointer semantics makes it difficult for developers to maintain a clear mental model of state ownership. These factors create a direct path to the subtle, hard-to-track data races that frequently appear in large-scale Go applications. Go closures transparently capture free variables by reference. This behavior is particularly important to understand when working with for loops. In a typical range loop, the loop variable is a single entity that is updated in place on each iteration. If we look at the racy code example on the left, we see Go routines being launched inside the loop. Because these closures capture a reference to the same job variable, they end up racing to read it while the loop is concurrently updating it. This often results in Go routines processing the wrong data, or even the same final item multiple times. To fix this, we look at the corrected code on the right. Here, we use the idiomatic fix of shadowing the variable. By declaring job equals job inside the loop body, we create a new variable instance for every iteration. Each Go routine then captures its own unique copy, resolving the race condition and ensuring that each job is processed correctly. Race conditions can often hide in plain sight within Go's built-in types, particularly slices and maps. While the array-style syntax of map access might suggest that concurrent operations on different keys are disjoint and safe, the underlying reality is different. Go's built-in map type is not thread-safe for concurrent reads and writes. As shown in the code example, launching multiple Go routines that write to the same map simultaneously creates a significant risk. This is because modifying a map, such as adding a new key, can trigger a reorganization of the entire internal data structure, leading to a race condition with any other concurrent access. To avoid these issues, always protect concurrent map access with a sync.mutex, or utilize the purpose-built sync.map for thread-safe operations. Understanding the distinction between value and pointer semantics in Go is critical for avoiding subtle but dangerous bugs, particularly when dealing with concurrency. In Go, sync.mutex is defined as a struct, which is a value type. This means that if you pass a mutex by value to a function, you are creating a completely independent copy of that mutex. Looking at the incorrect example on the left, the critical section function accepts m as a sync mutex value. When we launch two Go routines in the main function and pass the mutex directly, each Go routine receives its own unique copy. Consequently, when each routine calls m.lock, it is locking its own local copy, which provides absolutely no protection for the shared variable a. This leads to a race condition because both routines can enter the critical section simultaneously. On the right, we see the correct implementation using pointer semantics. By changing the function signature to accept @syncMutex, we ensure that the function receives a pointer to the original mutex. In the main function, we pass the address of the mutex using the ampersand operator. Now, both Go routines are referencing and locking the exact same mutex instance. This properly synchronizes access to the shared data, ensuring that only one Go routine can increment the variable a at a time. The key takeaway is that synchronization primitives should almost never be copied. They must be shared via pointers to maintain their state across different parts of your program. Analyzing a dataset of over 1,000 fixed data races at Uber reveals distinct patterns in how these concurrency bugs manifest. As the chart illustrates, the single largest category is missing or incorrect locking, which accounts for 472 cases. However, issues deeply tied to Go's specific language design represent a massive portion of the total. Concurrent slice access is the second most frequent cause, at 391 instances, highlighting the complexities of managing slice headers across multiple Go routines. Furthermore, we see 139 cases occurring in parallel test suites, 121 due to accidental capture by reference, and 125 involving other language nuances, such as map behavior and value versus pointer semantics. These results underscore that while traditional locking mechanisms are vital, preventing data races in Go requires a specialized focus on the language's unique memory model and data structures. To effectively conquer data races, we must adopt a multi-layered strategy that moves from reactive fixes toward proactive design and, ultimately, performance mastery. This framework is structured into 3 progressive stages. At the foundation, Layer 1 is Detect. This phase focuses on building a robust safety net by implementing continuous, automated race detection. By identifying issues early in the development lifecycle, we establish a reliable baseline for code quality. Moving up to Layer 2, the focus shifts to Prevent. Here, we leverage Go's native toolkit to design and implement race-free code from the very start. By making concurrency safety a fundamental part of our architectural design, we proactively eliminate risks before they manifest. Finally, Layer 3 is Master. At this level, the goal is to optimize memory allocation to enhance both correctness and performance. By mastering how data is handled at scale, we ensure our applications are not only safe, but also highly efficient. Together, these layers provide a comprehensive path toward building high-performance, concurrent systems with confidence. Layer 1 of our strategy focuses on systematic detection at scale. At Uber, we manage a massive Go monorepo with over 100,000 unit tests. To identify data races, we periodically run this entire suite with the Go race detector enabled. Once races are detected, they are automatically deduplicated to ensure we aren't overwhelmed by redundant reports. These unique issues are then logged as JIRA tasks and assigned to the relevant code owners using specific heuristics. Our process follows 3 key principles. First, we automate detection across the entire codebase to ensure comprehensive coverage. Second, we perform this analysis post-merge. This is a critical decision because the race detector's non-deterministic nature and high overhead, often 2 to 20 times the execution time and 5 to 10 times the memory usage, would make CI builds flaky and slow if integrated directly into pre-commit checks. Finally, we use heuristics to drive accountability and ensure fixes are implemented. While this detection layer is highly effective at catching existing bugs, its significant performance cost and the reactive nature of the process make prevention a far more desirable and efficient long-term goal. Layer 2 introduces the Prevention Toolkit, which is built around the sync package. Go provides a powerful set of primitives in this package, specifically designed to help us write correct, race-free concurrent code. First, sync.mutex and rwmutex provide mutual exclusion to protect shared resources from simultaneous writes. You should utilize rwmutex for read-heavy workloads to improve performance by allowing multiple concurrent readers. Next, sync.waitGroup is used to block a Go routine until a collection of other Go routines have completed their work, ensuring that all parallel processes finish before the program proceeds. For specialized data handling, sync.map provides a thread-safe map. It is most effective for specific use cases, such as grow-only caches or when different Go routines access disjoint sets of keys. The sync/atomic package provides low-level atomic memory primitives for simple types like integers. These allow for thread-safe operations while avoiding the overhead of a full mutex lock. Finally, sync.once guarantees that a specific function is executed exactly one time. This is highly useful for initialization routines that must only occur once during the application's lifecycle. Moving into Layer 3, we shift our focus from basic correctness toward high-level performance. True mastery of Go requires an understanding of how the language manages memory, specifically where variables are stored. Every variable in your program is allocated in one of two places, the stack or the heap. The stack provides fast per-Go routine memory. Allocation here is incredibly efficient, essentially requiring only a simple pointer bump. It is automatically cleaned up as soon as a function returns, though it is limited in size. In contrast, the heap is slower, shared memory used by the entire application. Allocation on the heap is more complex and relies on the garbage collector to reclaim space, which introduces additional CPU overhead. To balance these two environments, the Go compiler performs escape analysis at compile time. This process automatically determines if a variable can safely reside on the stack for maximum performance, or if its lifecycle requires it to escape to the heap. By understanding this mechanism, you can write more efficient code that minimizes unnecessary pressure on the garbage collector. Go's escape analysis is intentionally conservative to guarantee memory safety. This often leads to variables being moved to the heap even when they could safely reside on the stack, particularly when pointers are passed to interface arguments. We can manually intervene to prevent this unnecessary heap allocation. By converting a pointer to a UNTPR, which the compiler treats as a simple integer, we break the chain of references that the compiler's escape analysis tracks. In the standard code example on the left, passing the address of obj directly causes it to escape to the heap. In contrast, the optimized code on the right shows the address being stored as a UNTPR. Because the compiler only sees an integer being passed, the variable obj stays on the stack. We then convert the UNTPR back to a pointer at the call site. Using this method effectively tricks the compiler, allowing for more efficient memory management in high-performance Go applications. The impact of this optimization is most visible in the drastic reduction of heap allocation. By preventing large objects from being unnecessarily allocated on the heap, we significantly lower memory usage and decrease the pressure on the garbage collector. As the comparison shows, heap allocation fell from 41,864 bytes to only 872 bytes. Similarly, the total heap in use decreased from 57,344 bytes to 16,384 bytes. This shift represents a major gain in resource efficiency and overall application performance. The path to Go engineering excellence begins with a deep understanding of its unique concurrency challenges. We started by identifying the primary problem, the hidden risk of data races. We then examined how Go's own idiomatic patterns can sometimes make these races subtle and common, complicating the development process. To navigate this, we have built a solution framework focused on 3 pillars: detect, prevent, and master. Writing robust concurrent code is a cornerstone of engineering excellence, and the concepts we have covered are central to mastering the complete Go lifecycle. On our roadmap to excellence, we have specifically highlighted memory model and escape analysis to ensure a deep grasp of resource management. We also prioritized comprehensive testing strategies, including unit and integration testing, with a dedicated focus on race detection. These foundational steps are critical for building reliable, high-performance applications as we continue our journey.